Have you ever wondered how a box in your kitchen can boil water in seconds without any visible flame or red-hot coils? It's not magic. It's high-power radio frequency engineering. Today, we're going on an 8-minute deep dive into the hidden physics that makes your kitchen run. We often take the microwave for granted, but it's actually a repurposed weapon of war that uses the same principles as the radar systems that defend our skies. From vacuum tubes to molecular resonance, we're tearing down the mystery to see what's actually happening at the molecular level. At the heart of every microwave is a component that sounds like it belongs in a sci-fi movie, the magnetron. To understand it, we have to look back to the 1930s when engineers were trying to find a way to detect enemy aircraft using high-frequency radio waves. They needed a compact, powerful source of radiation. The magnetron is essentially a high-powered vacuum tube. It uses a central cathode that, when heated, boils off electrons into a surrounding vacuum, but instead of just traveling in a straight line, they are forced into a circular dance by powerful permanent magnets swirling around resonant cavities. As these electrons whirl past the openings of copper cavities, they induce a resonance, much like blowing across the top of a bottle. The physical dimensions of these cavities are tuned precisely to the 2.45 gigahertz frequency, creating the oscillating electromagnetic fields that give the microwave its power. Why 2.45 gigahertz? It's a balance. Higher frequencies would heat only the surface, while lower frequencies would pass right through the food. This specific frequency was also chosen because it doesn't interfere with communications like cellular networks or early radio systems. These waves don't just radiate out, they are guided. A metal pipe called a waveguide directs the energy from the magnetron into the cooking chamber. The dimensions of this pipe are critical. If they were even slightly off, the waves wouldn't travel efficiently, bouncing back and potentially destroying the magnetron itself. The target of these waves is the humble water molecule. Water is a dipole, meaning its charge is distributed unevenly. The oxygen side is slightly negative, while the hydrogen side is positive. This makes it highly responsive to electromagnetic fields, like a tiny magnet reacting to a changing polarity. Because the field flips 2.5 billion times a second, those molecules try to stay aligned, spinning and flipping back and forth at that same staggering rate. This results in billions of molecular collisions every second, creating the friction which we experience as heat. It is molecular agitation on a massive scale. Here's a mystery. Ice doesn't heat well in a microwave. In a solid state, water molecules are locked in a crystal lattice and can't flip freely. This is why a frozen burrito stays ice cold in the middle while the edges burn. The waves are passing through the ice without being absorbed. Once a small amount of water melts, the liquid water absorbs energy rapidly, creating heat. Through the process of conduction, that kinetic energy then spreads to the surrounding frozen parts, proteins, and fats. This is why moist food cooks so much faster than dry items. The water is the primary energy conduit. Microwaves actually don't cook from the inside out. That's a myth. Due to the skin effect, the energy only penetrates about 1 to 2 centimeters into most foods. The interior is heated solely by conduction, the outer layers passing their heat inward. This is why thick items need time to rest. Microwave energy isn't perfectly uniform. As waves reflect off the metal walls, they interfere with each other, creating a pattern of standing waves. Some areas receive double the energy, hot spots, while others receive almost none, known as cold spots. Without a solution, your food would be half boiled and half frozen. To solve this, engineers added the turntable. By moving the food through the stationary wave pattern, we ensure that every part of your meal eventually passes through a high-energy hotspot. This mechanical solution compensates for the physical limitations of standing wave interference. The mesh on the door is a masterpiece of engineering called a Faraday cage. It's designed so that the holes are much smaller than the wavelength of the microwaves. To the radiation, that mesh looks like a solid wall of metal it cannot penetrate, even though it looks transparent to our eyes. Visible light has a wavelength of about 500 nanometers, so it passes through the mesh with ease. But microwaves have a wavelength of 12 centimeters. They are physically too large to fit through the holes, keeping all that intense energy trapped safely inside while allowing you to watch your dinner cook. Safety is further ensured by redundant interlock switches. These prevent the magnetron from ever firing while the door is open. There are usually 3 separate switches, and if even one fails to engage, the entire circuit remains open, protecting you from any accidental exposure to radiation. In 1945, Percy Spencer was working for Raytheon when he stood near an active magnetron. He didn't feel anything, but he noticed a chocolate bar in his pocket had turned into goo. Instead of worrying about his health, he immediately saw a new way to cook, and the first microwave was the size of a refrigerator. Traditional microwaves can't actually dim their power. When you set it to low, the magnetron is still running at 100%. It's just clicking on and off. This is called pulse width modulation. If you set it to 50%, it simply cycles 5 seconds on and 5 seconds off to achieve an average power level. Modern inverter microwaves are a major upgrade. They use electronic power supplies to actually lower the magnetron's output, providing a constant, low-intensity stream of energy. This prevents the edges of your food from boiling while the center is still defrosting, making it far superior for delicate cooking tasks. This whole process is known as dielectric heating. Materials like plastic, glass, and ceramic have low dielectric constants and few dipoles. This allows the microwaves to pass right through the container, focusing all their energy solely on the water inside the food itself rather than heating the plate. Metal, however, is a conductor. Microwaves create high-voltage electric fields that cause electrons to move across the metal surface. On the smooth interior walls, it's fine, but sharp points on crinkled foil can cause the electricity to jump through the air, creating the arcs and sparks you've seen in fail videos. Superheating is a fascinating but dangerous phenomenon. In a very smooth glass, water can exceed 100 degrees Celsius without boiling because there are no nucleation sites for bubbles to form. One stir can then trigger an explosive, instantaneous boil-over. Always be careful with liquids in the microwave. Microwaves are efficient because they heat only the food, not the air. And to be clear, they use non-ionizing radiation. It cannot damage your DNA or make food radioactive. The moment the door opens or the timer stops, the waves vanish instantly. It is safe, efficient, and quite frankly, a modern marvel. From radar technology to the molecular friction in your dinner, the microwave oven is an absolute masterpiece of physics and electrical engineering hidden in plain sight. It transformed how we live and eat, all through the simple rotation of a water molecule. If you enjoyed this deep dive into the engineering of the microwave, hit that subscribe button and join us for our next journey into the machines that run our world. Thanks for watching, and stay curious.